This is the D1 Decision 1 exam from 2020. Let's just do it. So, the easiest 2 marks in probably all of A-level further maths is just to figure out from this table that D connects to A, B, C, and F. So you're going to draw some lines to those, and then you're going to label them with these numbers. Oh, wow, that was complicated. B, use Kruskal's, whatever, however you say that name, his algorithm to find the minimum spanning network. So you have to be a bit careful here to actually do this exactly the way we want it. The mark seems quite harsh. So we just look in the table and we find the absolute smallest value, which I think is from A to D, because that's 22. Then we look for the next smallest, which is A to B. Now we've got to be careful of a couple of things here. Firstly, you're not allowed to create any loops, so we can no longer use B to D. Although it only wants you to mention that a bit later on, not right away. But just bear in mind, we're not allowed to use B to D. And also bear in mind, we probably, sorry, I'll say that in a second. But yeah, A to B is 24. And then 25 is B to C, which I can use without creating a loop, so that's fine. Look for 26s, there is one, C to G. That's not going to create a loop at all, so that's good as well, I'll use that. 27 is B to D, so that's when we're not allowed to say we can't use B to D. That would be the next one in the algorithm, it's the next smallest, but we can't use it, it would create a loop here. So we'll reject B to D. Can we see any 28s? Probably not. Can we see any 29s? We can. E to G. That doesn't create any loops either, so I'll take that. And I think the only one we haven't been to, A, B, C, D, E, F, G, the only one we haven't been to is F. So at this point, what the algorithm does is you just keep going up, but actually if you want to cheat a little bit, you can just look for the smallest one in the F column, which is F to C. But we do have to mention we want to reject all the ones below 36 in length, between 29 and 36, even though it seems stupid to have to say this. We're going to reject C to E, but mostly because we've already been to C and D, so we don't need it. So we'll reject that. We'll reject C to D, which is also smaller, and we'll also finally reject A to E, which is also smaller, and we'll finally get to 36, which is F to C, and now we've got all of our things. State the minimum weight. So you just, I mean, what I would have probably done if I was doing this on paper is just write down the numbers to these underneath each one. But I mean, these are all the numbers that we referenced, and they add up to 162. And that's the first question done. Question number 2 then. So we've got, this is what it's a critical path analysis question, is that's what it's called or something like that. Explain why each of these dummy activities, these are the dotted lines, each of those are required. This one's required because we need to demonstrate or show in some way that H is dependent on B and C getting done, whereas F and G are only dependent on B. So we use this dummy variable to get down to here to be able to show that in the picture. And this one here, we've got to end all of the activities at one point, but K and L start at the same point because they're dependent on the same activities, which means if we didn't use this dummy variable, K and L would just take up this same space, which they're not allowed to do. So this one just allows us to see K and L and separate them out. B, complete the table in the answer book. So these are the precedency tables here. So A, B, C, clearly not dependent on anything. D is dependent on A. We're literally just looking at which arrows come before the arrows in the letter here. E is dependent on A as well. F is dependent on B, so we'll put that in. G is dependent also on B. H is dependent, as we referenced, on B because of this dummy variable and C. I is dependent on, where is it? There it is. No, it's not. Where's I? There it is. I is dependent on E and F. It's also, of course, dependent on some of the stuff that comes before it, but we don't care about that. Immediately preceding activities is what we care about. J is going to be G and H, and then we've got K and L to go, which are both dependent on D and I, and we'll finish up that. Good. Complete diagram 1 to show the early event times and the late event times. So that's this diagram here. So when we're doing the early times, we'll start here and we'll take the longest time possible to get to each of these points here. So, I mean, obviously this is a 6, and this is going to be a 7 here. It's tempting to just write a 5 here, but like I said, we're looking for the longest time possible to get to here, and that would be a 7 plus 0, dummy worth 0, so that would be a 7. Then to get to here, maybe it's going to be either 7 plus 3, which is 10, or 7 plus 4, which is 11, so we'll go with 11, that's the biggest. Here is going to be 7 plus 3, or 6 plus 5, 6 plus 5 is bigger, that makes 11. And then of course 11 plus 4 is 15, or 6 plus 4 is 10, so we'll go with the 15. 15 plus 5 is 20, that's the only thing that can go there. 15 plus 6 is 21. 20 plus 0 is 20, so we'll go with the 21. Then going backwards, exact opposite, you go to 21 again, and then you go for the minimum amount of time you can go backwards. So clearly 21 minus 0 is still 21. 21 minus 5 is 16. 21 minus 6 is 15. We'll go with the minimum, which is 15. Minus 4 is 11. Minus 5 is 6, but 15 minus 4 is 11. We'll go with the smallest, which is 6. 11 take 3 is 10, and that's the only way to get there, I believe. Oh no, it's not, because of this whole thing that's going on here. So let's go down here next. 21 minus 6 is 15. That's the only way to get there. 15 minus 4 is 11. 11 take 3 is 8, so we'll take the 8 there, actually. And then 15 take 3 is 12, so we'll go with 12 and 8, and that'll be the entire picture, I hope. State the minimum completion time is obviously 21 just there. And the critical activities are activities that go from boxes that have the same number in both. So that would be A, D, E, and L. So activities that go from a box with same number in both to a box with the same number in both. So this, and this. Except D isn't, because you also need this amount of time to be the same as the distance between these things. So 0 and 6 are 6 apart. Activity takes 6. These two are 5 apart, activity takes 5. These two are 9 apart, activity only takes 4, so that's not critical. So it's just going to be A, E, I, and L for our critical activities. This question goes on a bit longer. Each activity requires one worker. They want us to draw a resource histogram for this. So here's what they give us. I'm going to do this very shadily just because I absolutely couldn't be bothered to do this properly in PowerPoint. But we'll start with the activities A, B, and C. B takes 7 hours, A takes 6 hours, C takes 5 hours. Now what you want to do is you want to break this up into, like, you want 7 Bs in each hour, but I couldn't be bothered to do that in PowerPoint, so I'll explain how I'm going to fix this later. I'm just going to do solid bars for now. When C finishes, you can start activity H, which I'll just put down here. Actually, no, H needs B to complete as well, so I'll start H once B is done there. Okay, so that's fine. When A is complete, we can start D and E, so we may as well just put those two there. Now, E can't be completed until A finishes, so that's there. C doesn't actually, when you finish C, you can't actually start anything else because you have to wait for B and A to be done, so there must be a gap there. Okay, after that, of course, I'll explain that in a second. G and H get to here. You can now start, well, we haven't done G yet, actually. We also haven't done F, but we have finished B, so we can do those now. So let's start G and F as soon as possible. As soon as B finishes, we'll start G and F as well, using more workers. We'll just start those as soon as possible. So now, once H gets done, we have to wait a little bit for G to get done before we start J. So I'll wait for that hour before we start J. We have to wait until F and E are done before we start I. So that's going to have to also start just after E's finished. And then we can finally, once I is finished, we can start K and L. So we're going to stack those up over there maybe. And that will finish within the 21 hours. Now this isn't how this usually gets drawn. What we're going to do, like I said, you want to put 7 singular B's here. This is the answer in the book, so let me just explain. This G and this E person can drop down to here to fill in this gap here, and then these K's can drop down to there, and these L's, if they're all separated, can drop down to there, and this one can drop down to there. So this is the correct picture. I just couldn't be bothered to draw it exactly that way. It doesn't matter what order you stack these letters in. So I think my answer is fine here as long as I bothered to drop those down. I just couldn't be bothered to put in so many separate boxes into PowerPoint. It would have just driven me absolutely insane. So anyway, let's use that answer from here. Determine whether or not the project is completed with fewer workers than indicated here. Now 5 workers are indicated here. It feels like you can probably do better than this. Let's focus on this stack here of 4. H only takes 3 hours. And actually, if you do the what's it called? I've written it down here, haven't I? The float time. 15 take 3 take 7 is 5. I believe. So H has a float time of 5, which means we could delay H by up to 5 hours. Now we don't need to, we could just delay it by 3 hours and put it down here, and that takes off this worker, and now we just have 4 workers. And J is allowed to be delayed by those 3 hours, right? Because then it would still finish. If it started at hour 14, it would still finish at hour 20. So we just move J along, and that doesn't, because the J's are still being used here, that wouldn't ever get this up to 5 workers at all. So that's fine. So delaying H will get us down to 4 workers in total. Now, it's only worth 2 marks, so I reckon you get a mark for saying, yeah, you can break it down to 4 workers. Sorry, this should say 4. Apologies, this should say 4 here. I might just go in there and edit that, because why not? So only using 4 workers, and it's tempting to say, oh well, maybe it could maybe you could do it in 3 workers if you move these g's around. The problem is, g does also have a float time, right? 15 take 4 take 11. But even if you make it later, you're now just interfering with h, and you still have 4 workers here, and you can't move it so late that it's only going to have 3 here. So it seems very unlikely. The lower bound, by the way, if you calculate the lower bound, again, it's only worth 2 marks, so you don't have to. But if you add up all of these numbers here and then divide by 21, you get a lower bound of 2 point something. So the lower bound is 3 workers, but I don't think it's feasible. And we've already picked up the mark for just saying, yeah, you can drop it down to 4 workers by doing this. And yeah, so we don't have to be too careful about the rest of it. Anyway, question number 3 then is about a directed path like this, so that's quite cool that we've got a direction here. Just be careful, because that's going to mean that these tables aren't symmetrical with this direction here, so that's gonna make it a bit more, we have to be a bit more careful here. So set up the initial route, so just look how long it takes to get to A to all of these things. So from A to these places, from A to B is 8, and then A to C is 4, A to D is 7, and then you actually can't go from A to E without passing through anything else, so we just call it infinity. And then B to A is again 8, and I won't go be too careful. You can do this one symmetrically, you just can't do the rest of them. So B to C, for example, is 3, B to D you can't do in one go, so it's infinity. B to E is 10, and then C to B, again, those are symmetrical, so we never use this one. But C to D is this is where it's have to be a bit careful. C to D we can't do, so that's infinity. C to E is 6, but then D to C we can do, that's 1. So that's where the non-symmetry happens. And then D to E is 1 as well, and then we can just fill in these last bits there. So that's good. So that's the initial matrix. That's 2 marks. Perform the next 2 iterations of Floyd algorithm. So let's get these tables out here. So they've done 2 iterations already. So they've presumably searched from A and from B. And you can kind of see in this table with the things being replaced with A's and B's that that's exactly what they've done. So the next one we should do is search through the C's. So let's keep this C row and column locked, and then let's go across and go, okay, well, A to B, our best time is 8. If we go via C, can we improve that? Well, A to C is 4, plus another 3 is 7. So yeah, we can improve that if we go through C. So I'll put a 7 here, and I'll say we're going through C to get there. A to D, our best time is currently 7. A to D, can we do it better through C? Well, I don't think so, because of this direction bit here. So we'll just keep that at 7. And then A to E, our best thing is 18. That seems likely that will improve. Go down to C, and then go to E. That makes 10, so that's also through C, so we'll update that bit as well. From B then, so B to A is currently 8. That's our best time. If we go via C, and really you should be using the numbers in the tables rather than the graph itself, but I mean, it's very natural to use the graph, isn't it? So if we go from B to C first, so that's from B to C is 3, and then plus C to A, that's 4, which makes 7, which is less than 8. So we can do it with this 3 and this 4, which we can see from the graph as well. B to C to A is 7, sorry. And we also had from here as well, because it doesn't use the directed bits. That's good as well. So that also goes through C. And then B to D. B to D we can go through C maybe. Well, that's unlikely to work because of this directed bit here. So that I think, oh, in fact, it does work. 14. How do we get there? Yeah, we go to C. So yeah, this is why you want to use the table, isn't it? So B to C is 3, and then C to D is 11. Add those together to get 14. That's less than this. So you don't even need to look in here. You just want to use the numbers in the table. That's the safest thing to do. So that changes to a C as well. And then B to E. So again, let's think about C to E. That's 6. Sorry. B to E, C is 3, plus C to E is 6. That makes 9, which is less than 10. So that will work as well. So we'll change that. Keeping on. So D to A. Well, again, D to C is 1. So this seems like a very good row that will change a lot of things. D to C is 1, and then C to A is 4, so that makes a total of 5, which is less than 7, so we'll go through C there as well. D to C is 1, plus C to B is 3, and that makes 4, so that's a massive improvement on this. So we'll replace that with this thing. And then D to E, well, D to C is 1, and then C to E is 6, that makes 7, but that's not an improvement on 1. Very hard to improve on 1, so we'll keep that the same. And last column, E to A, well, E to C is 6, and then C to E is also 6. Sorry, C to A is 4. 6 plus 4 is 10, which is less than 18, so we'll go with that. We'll change that. E to B, E to C is 6. C to B is 3. That makes 9, which is less than 10, so we'll update that. And then finally C to D. C to C is 6, plus C to D is 11. That makes 17, which is not an improvement on 1, so we'll leave it alone. Okay, so that's one iteration done, and then we'll do the second iteration using D as our locked column. So copy that column, copy that column. I've just kind of copied this into here, and I'm gonna update anything that needs updating. I'm gonna be. Can I just skip through this and not narrate it because I can't be bothered? We just do exactly the same thing, right? Exactly the same thing. Just try finding any roots. As soon as you find one that's better, for example, A to E is 8 because via D you can go A to D is 7, and then D to E is 1 plus those together to get 8 is less than 10. I've said this many times, so I'm just gonna. If you want to have a think about them first and calculate them, you can do. Otherwise, I'm just gonna roll through it, and we get all these. These two rows don't improve anything because B to D and C to D take so long that going via D is never going to be a good idea. Whereas this column, because E to D is only 1, lots of stuff gets improved there. In fact, I think all of it does. That's fantastic. We have 2 iterations done. And then they're saying if they do they've done the final iteration themselves, and and got to here. So this is the optimum matrix that we've got here, using nearest neighbor algorithm, starting at A, find a Hamiltonian cycle. So we start at A, we go to its nearest neighbor, which is, we should really be moving this way because it's A to these ones is from here. So start at A, nearest neighbor is C, which is 4 away, and then from C, nearest neighbor is B, and this is why it's important to read from here to here, read across the rows first, because if you read downwards, you'd think C to D was 1, but of course it isn't because of this directed thing here. So read across, nearest neighbor from C is B, nearest neighbor from B is C, but we've already got that one, we've already got A as well, so we go to E next, and then nearest neighbor from E, well the only one we haven't got is D, which is 1, and then we have to go back to A from D, which takes 5. And we add all those numbers together, we get 22. Interpret the cycle in terms of actual villages visited. A little bit confusing as to what this even means for a second, but what it actually means is that sometimes these journeys don't go straight from one to the other. That was the whole point of Floyd's algorithm, was like A to C is 4, and that's just going A to C, and C to B is 3, and sure, that's just going C to B. But B to E, which is 9, isn't just going B to E, that's going B to C to E. So this journey is actually A to C to B, back to C, then to E, and then E to D is just 1, so that's fine, and then D to A, you go back to C again, then to A. So this is the actual journey that's being done. And yeah, that's that question done. This is the easiest question of all time. My year 7s can literally do this. We just need to say where is R? Well, it's less than this one. It's greater than this one. I've done this in a different order, but so less than or equal to signs for here, greater than or equal to sign there, and then less than or equal to sign for this one. And yeah, cool. The objective is to maximize P, where P is this. Now, you could do that sort of slidey thing. I discovered that literally the only worthwhile thing that a set square does is allow you to do the ruler trick along the side here. Of course, no, I don't understand why you would ever do it, because you could just check the vertices, which is much quicker, just much easier and much more mathematical, to me at least. And that's what it's telling you to do here. So just check these 3 vertices. So first, of course, we just need to find where these vertices are, so set this one equal to this one. Well, maybe we just have to rearrange that for y first. Then set it equal. It wants it exactly, I mean, we've got calculators, so it doesn't take an immense amount of brain power to do this exactly. You just type everything into a calculator and just leave the answer as fractions, and resist the urge to press the SD button, like a pleb. So anyway, we get this. So that's the profit at this point here. Just taking that point and something in there. Then we set maybe this line equal to this line. Is that what I did next? It is. Rearrange this for y, I guess, first. And then we find another x coordinate. We get a corresponding y coordinate. And then that's that coordinate there. We plug those values into here to find a p, which is this. So that's the profit at that vertex. And then here we set this one equal to this one. So that's our final job. We get this coordinate for x. We get this coordinate for y. We plug it into here. We get this value. This one turns out, once you do press the SD button, to be the biggest, and so the optimum vertex is this last one we found over here. Then it says, this is quite an interesting question, the objective is changed to this, so the line is a slightly different gradient that you'd slide up here maybe. Given that the optimal vertex is still this one, find the values of A. Essentially what that just means is that if you put this x and y into here, that's bigger than when you put this x and y into here, and it's also bigger than when you put this x and y into here. And we can just say that. We can just say, okay, that means that x and y in here bigger than these 2 x's and y's in here. And that will just create an expression for A for us, which is this. And then we can say, well, it's not only bigger than this one, it's also bigger than this one. So we put those in, and again, we just do some maths and we get this, and then we say, okay, yeah, it must be between those 2 things. And yeah, we have question 4 done. Question 5 is the question on these packing algorithms and stuff. They often ask this kind of thing. It's actually quite interesting. Or not interesting, but I don't know. Is it interesting? Who cares? So first bin packed thing with this. So 23 goes in there, 17 goes in there, 8 goes in there. So that's fine, except that means we have to do it in order, right? So 23, then 17, then 19 goes in there. Okay, then X also goes in here. So, and then 24 goes over there, and then so on. Now, this is bin size 50, so that means 19 plus X plus 10 is less than or equal to 50, which gives you this. And then you just have to read that these numbers are distinct. So X can't be 21, because then it's the same as this. So X has to be less than 21, strictly, which is where this inequality comes from. And then to get the other one, again, you sort of do this in order, I guess. And you say, well, what happened was 23 went in, 17 went in, 19 went in. Then the X had to go somewhere. But the X didn't go here, right? So what that means is, well, 23 plus 17 is 40, so that means X is bigger than 10. But also, so 19 and X and 18. So the X went up there, and then the 24 went here, then the 8 went there, then the 18 could have had a choice to go here, but it didn't. It went there, which means 19 plus X plus 18 must have been too big. That's why the 18 had to go here. So we sort this out and we get X is bigger than 13, and that's where both ends of the inequality come from. So that's cool. So maybe just write down some of the things that I said out loud, I guess. Maybe a bit more clearly than I said them out loud, because I was not clear, I don't think. We're going to do a bubble sort. So this is the first situation. So bubble those two. Nothing happens because we're going descending order. Bubble these two and we swap them over. Bubble these two, and it seems like nothing's happened, so that makes X less than 17. So that's fine. Bubble these two and we swap them over, it seems like, which is good. I mean, we already knew that had to happen. Bubble these two and it doesn't swap over, looking like it. So that means X is bigger than 8. And then I guess some more bubbling happens. Bubble these two, we swap them over. Bubble these two, we're going to swap the 8 with this. It doesn't really matter. We have this inequality, but we already knew that X had to be bigger than 13, so we just changed that back to the 13, and now we have this stricter inequality using the 17 here, which we learnt because these two didn't swap over in this bubble sort. When the first fit decreasing algorithm is used, so you could continue a bubble sort to get them into decreasing order, or you could just look at them and get them in decreasing order. So here they are in decreasing order. The 24 goes in, the 23 goes in, then the 21, then the 19. The 18 can't go with them, so it goes there, then the 17, then the X goes with those. So okay, this is still bin size 50. So let's just work out how much each of these bins has. So the first one has 47, the second one has 50, so that one is full. So this one is not full. So therefore 35 plus X is not 50, which means X can't be 15. Now looking at this, if X is an integer, X can only be 14, 15, or 16. Now it can't be 15 because that would make both these bins full, and it can't be 16 because that would make this bin have 51 in it, which it can't do. So that takes out both of those. And yeah, so X must be 14 via that logic. 6 is quite cool. So you've got this graph here with all these numbers. State with justification whether the graph is Eulerian. So a graph is Eulerian if it has no odd nodes at all, if all of the nodes have even degree, and it's semi-Eulerian if only 2 of them exactly have odd degree. And A has an odd degree, and so does G. They're both degree 3. So this is semi-Eulerian. There's a route from starting at A, finishing at G, or vice versa. And I think we can find it quite quickly. Like if we do maybe this. I think that worked. So semi-Eulerian, because it got exactly 2 odd nodes. Okay, next, the weights of the arc represent distances. X is between this and Y is between this. An inspection of minimum length that traverses every arc is found and has this. And it starts and finishes at A, so it must use every single thing here, and then it must use some of them again to get back to A. So wherever it finishes, it must use some of those again and get back to A, and that's length 409. It's also given the shortest distance from F to G, but you have to go via A as this. Using appropriate algorithms, find X and Y. Now, it's trying to be coy here. It's trying to say, oh, you've got to think of the algorithms yourself. You don't have to, for 2 reasons. Partly because Dijkstra's algorithm will be on every single D1 paper you ever do, and it hasn't come up yet, and it's certainly not in the last question if you look ahead. So it's definitely going to be a Dijkstra's algorithm question. And also because if you look in the answer booklet, this turns up, which is the setup for Dijkstra's algorithm. So yeah, we're going to be doing that. A starts at 1, 0, and then we say, okay, this is our working bar, 24, 42, and 65. The smallest is 24, so that will be the second one we go to, and we'll say 24. And then we go to all the other ones, so 24 plus 15 is 39, which of the smallest here is there here, which is, 39 is it, so that's going to be a 3, 39. And then we add 39 to all of these three to get to our next three things, and this one as well, actually, we can go backwards. So 39 plus that, 39 plus that, that, and that. Look for the smallest that you haven't been to yet. It's this one. So that's going to be our fourth one we go to with a 58. 58 plus x goes here. Just going to put it underneath because I can't fit it all in the bars. Which is the smallest here? Now look at the conditions again. X is bigger than 12, so that's bigger than 70. So 60 is going to be the next smallest. That's going to be the fifth one we go to with 60. Do 60 plus 34 and 60 plus y to get some more stuff here. And now which is the smallest here? Well, x is less than 26. In fact, y is less than 10, so this is definitely less than 70. This is bigger than 70, I think we just said. So I think this is going to be the next smallest, y plus 60. And then finally this one, which is bigger, 94 or 58 plus x. Well, if you put x as 26 in, you get to 94, I believe. So 58 plus x is definitely smaller. And I think we're going to have that there as our last one we go to. So that's most of the marks for the question done, just for performing that correctly. Now let's figure out what the rest of this means. It's given the length of the shortest route from F to G via A is this. Now essentially what that means is you go from F to A in the quickest way possible, which we know is this, right? We know the quickest way to start here and get here is 58 plus x. And then you go from A to G in the quickest way possible, which we know is this. That's the quickest way to get to HG. So therefore this plus this is the 140. That's the quickest way to get to A, and that's then the quickest way from A to get to G. So that's going to be 140. So we can sort that out when we get this. So clearly we need another equation from somewhere, and it's going to be from this one, obviously. So like I said, 409 represents traversing every road and then going from A to wherever you finished and back to A from wherever you finished. Now, from this first thing we said, if you start at A, because this is semi-Eulerian, you have to finish at G because those are the odd ones. So we're going to add up all the roads, and that gets us to G via our semi-Eulerian path. Then we're going to go from G back to A in order to finish at A. So therefore, the sum of all the paths, which is this, plus the shortest way to get from G back to A again, which is this, equals 409. And we can sort all that out, and we get this. We can do this one minus this one, and we get this, and then we get this, and that will be the entire question done. Just a really, genuinely, a really nice question. And Decision doesn't do that very often. But this actually required some thought, and it was good, because that's nice. Question 7 is obviously the simplex algorithm question. You'll always have one in the D1 papers. It's quite a long question, so we'll just break it down and do, this part first, then this part down here. So okay, it's going to be a two-stage simplex method, so we're going to need both some slack variables and some, I can never remember the name. I always think arbitrary, but it's not, is it? It's whatever it's called. Arbitrary architect? No, it's one of the A's. I can't even remember what the name of the A's are. Who cares? Who needs words? It's fine. Just read the coefficients. X plus 2y plus 3z plus s1 is equal to 45, so therefore if we're going to use inequalities, we're just going to ignore the slacks for a while and use less than or equal to. Now the second row uses these A's, so therefore it was a greater than or equal to inequality in the first place, so 3x plus 2y is greater than or equal to 9, and then we take away the slack and add in the A, whatever A stands for. Who cares? It's bothering me so much that I can't remember the word. Artificial. There it is. Artificial. Brought that out from nowhere. Incredible. And then the last one is going to be minus x plus 4z. And then again, it's because it's got an artificial, so it's going to be greater than or equal to 4. And we're going to max this p of 2x plus y plus 3z is what we're going to max, because then when we bring those all to the other side and end up with a 0, these all turn negative, the coefficients. That's fine. So that's all the constraints. Good. Copy the value in the answer book. So what am I doing next? Oh, okay. So firstly, to get this, because to fill in this thing here, you need what A is. So A is the two artificials added together with a minus in front. That's just the thing that you do. We can rearrange both of these. I mean, maybe write both of these with the artificials in. Just be careful. This one uses S1 to make it an equals, so this one's going to be an S2, this one's going to be an S3, and these numbers don't correlate together, so just be careful of that. If you've done some practice, you'll have seen that before. But anyway, so to rearrange that for A1 and put it in there, rearrange this for A2 and put it in there, and we get this, and then we can sort that out and we get this, and then we bring everything over to the other side except for the minus 13 to get coefficients of minus 2, minus 2, minus 4, 0 S1s, 1 S2s, 1 S3s, and minus 13 at the end. And that will be that column filled in, or row, sorry, filled in. Good. So now it's told us that they've done 2 iterations of simplex and got to here. Show how this shows a basic feasible solution has been found. So the fact that A is equal to 0 here shows that a basic feasible solution is found, because that means the 2 artificials. But remember, A was equal to minus A1 plus A2. So if that's equal to 0, then that means the 2 artificials add up to 0, and that's good because it means they go away, or something like that. I don't really... You may have got the impression, and you're correct, that I neither completely understand nor completely care why simplex method works. You just write down these things every time, and you get the marks, because the mark scheme also doesn't care whether you truly understand how this works. You just need to write the same things down every time. Write down the basic feasible solution. So this is just where you have x equals 3, z equals this, s1 equals this, and then all the others equal 0 because you haven't got them. They're not in these rows. So that's fine. That's the basic feasible solution. And the profit is this. So, okay, we've shown that we can get a profit. Can we get a bigger profit than that? And the answer is yes, or p-value. I guess it's not really talking about profit. The answer is, of course, yes. And it's asking us now to do... Oh, it is talking about profit. Cool. And the answer is now asking us to do another iteration of the simplex method. So they've given us these tables. Let's just do another iteration here. This is the largest negative value. So we'll go with that and get rid of that. Once we do our theta values, we're going to do these 3 divided by these 3. And you're looking for the lowest positive value, and that will be your pivot point. This is the only positive value. It's just this divided by this, this divided by this, this divided by this. So therefore this will be our pivot point here. So okay, we want this to become a 1, so we'll times this entire row by 12 over 7 to make this a 1, and we'll turn that into an S2, because that's what we've solved for to get a 1 here. So that's good. So times this entire row by 12 over 7. I'm going to be a heathen and write fractions like this, just so they fit in the boxes. You end up with this, and that's what I've done, times by 12 over 7. Then I want all of these to be zeros, so I just do some summing and row operation stuff to make all these zeros. So, okay, if I do this plus a third of this row, this plus a third of that will get you a 0 here, so I'm going to do this entire row plus a third of the row that I just wrote down, or the row that I just wrote down divided by 3, I guess. You end up with all this. You can check my calculations in a calculator, because that's certainly how I did them. So this plus this divided by 3, this plus this divided by 3, this plus this divided by 3. Sorry, not this. This plus this divided by 3, and this divided by 3, and this divided by 3, and this divided by 3, using this row that I've written out here. I always make that mistake. Anyway, to make this into a 0, we're going to do this plus a 12th of this, I think. So this divided by 12. So next row, we'll have a z here. This plus this divided by 12, this plus this divided by 12. Sorry, this plus this divided by 12 is that. This plus this divided by 12 is that. This plus this divided by 12 is that. Is it? Oh, sorry, this divided by 12. Yeah, this divided by 12 is a 7th. So 0 plus 7th is a 7th. And so on, and you get this. And then finally, to make this a 0, you have to take this and times it by 11 twelfths, this entire row. And then do this plus 11 twelfths of this row will make this a 0. And again, just check my maths if you want to, but you get all these numbers if you eventually do that. So, you know, for example, this one is this here plus 11 twelfths of that, which is just 11 over 7. And then 0 plus 11 over 7 is 11 over 7. So we get this, and we get all those. And we've got all positives down here, so we found our optimal solution. All the numbers in the p row are positive. It's the value 69, which is nice. And then state the values of the basic variables. S2 is 63, x is 24, and z is 7. And those will be our basic variables. We don't have y just because we just happened not to create a y here. You just write down whichever ones are in this row here. I think that's the entire paper. Thank you for watching, and I'll see you next time.